everyone. I am Shivam and I am going to present before you this paper, which is Magnetic Field Dependent Photodynamics of Single NV Defects in Diamond. This is the paper by our professor Roch, and then we are presenting. So so the first let's have a look on the research motivation on this paper. So the NV centers are basically atomic sized quantum sensors in diamond. These are used in quantum computing, nanoscale magnetometry, and bioimaging. So the challenges for the ESR based magnetometry is as follows: like it fails at high magnetic fields or even misaligned magnetic fields, and we in this method we rely on microwave scanning to detect the frequency range and then calculate the magnetic field. So we also in this method in this research which has been carried out in this paper, we will have a look on the microwave free all optical field imaging of the magnetic field. So this is what exactly this paper proposes based on photoluminescence intensity and lifetime. So the NV center basics, as you all know, basically we have discussed this throughout this course. So this NV minus is like nitrogen atom plus the vacancy, which is threefold symmetric across the axis of the NV. And then the energy levels, these are basically the three triplet in the ground state, which is denoted by 3A2, the excited state triplet, which is 3E, and then the one singlet metastable state. So the optical transitions which take place here are when the spin is in ms equal to 0, then it is like the red photoluminescence at 637 nanometer, which is the zero phonon decay. And then the ESR detects the spin states optically, which means the photoluminescence is the basic thing which we are going to, which the ESR method relies on to detect the magnetic field. So the problem with ESR magnetometry is if you have the magnetic field aligned parallel to the NV center axis, then you will have a good magnetic field measurement, but also the spin states will not mix. We will see it in the Hamiltonian, which we will discuss in the next slides. And so when it is when it is parallel to the NV axis, when the magnetic field is parallel to NV axis, then we have a good contrast of magnetic field and better calculation of the magnetic field in that direction. But when it is aligned somewhere away, then and also we have some if we have somewhat higher magnetic field close to greater than 20 millitesla, then we have a difficulty in measuring the magnetic field using this ESR method. So the reason for those things are like the spin states mix. Basically, you have different components in the perpendicular direction, which adds on to the Hamiltonian, and then it creates different problems. So it corresponds to like the spin polarization decreases, and the ESR contrast also decreases because of this mixing. So as we discussed, 20 millitesla, beyond 20 millitesla, the ESR readout fails. And then we somehow have to design some optical magnetic readout method to measure the, even qualitatively measure the magnetic field. So this is the 7-level model equation for our system, which we are trying to propose here. So in this system, not going into the details, but when you solve the rate equations here, you will have some relation in which you will see that we will also discuss in the data that when we increase the magnetic field, the spin states mixing will increase, the non-radiative decays will also increase, and which will decrease the photoluminescence intensity. We can also interpret it as you increase the off-axis magnetic field, meaning the B perpendicular will increase, then the ESR contrast, photoluminescence intensity, and the excited state lifetime will also decrease. The ESR contrast is the basic, the main thing which we had relied before in the measurement of magnetic fields using the ESR method. So the experimental setup here is as follows. You can see here the confocal microscope here, plus the single nitrogen vacancy centers in the type 2A diamond, which is the very pure form of diamond. The magnetic field is also applied at the control angle theta, and then in this we try to measure the ESR spectra, time resolved photoluminescence, and the lifetime. The experimental observations, basically we are just trying to present here some of the data which has been discussed in the paper, and some of the data which enhances our claim of how we are measuring the magnetic field using this method. So the ESR contrast, you can see here, vanishes with increasing magnetic field. The effective lifetime also decreases with the magnetic field. Also, it has some dependence on angle, which you can see in the graph. The same is the case for the photoluminescence with increasing magnetic field and changing angles. So how are we measuring this qualitative magnetic field? So we are first attaching a nitrogen vacancy center to the AFM tip, which is atomic force microscope tip, and we are scanning across the sample, or the hard disk surface. So this we are doing it like that in the hard disk. We are scanning it across the hard disk surface. We are recording the photoluminescence lifetime, or the photoluminescence or the lifetime per pixel, as we saw in the previous data. And so some basic interpretation here is that darker areas correspond to stronger off-axis magnetic field. And the resolution here also you can see, which is in the range of 100 nanometers. So the results are as follows. Like, we have been able to, we were able to do this all optical magnetic field imaging, although qualitatively, but yeah. We measured the photoluminescence and lifetime maps, which correlate, meaning they were all decaying with increasing magnetic field, which reveals the off-axis magnetic field strength. We also saw that we were able to resolve the 100 nanometer features across the sample of the magnetic field, and we were able to qualitatively detect the 10 millitesla fields greater than 10 millitesla. The advantages of this method is that we did not use any microwaves. This technique is also non-invasive and works under the ambient conditions. So just to summarize, the ESR-based magnetometry fails at a higher off-axis magnetic field. The reason for that is the spin states get mixed, and the photoluminescence is like altered, or lifetime is altered. And these optical effects also enable, like the method which we proposed here is like we did the measurement qualitatively microwave free, and then we demonstrated the nanoscale imaging of the hard disk stray fields. Yeah, thank you. Hmm. Yes. And then if you polarize the sample in a different direction, so you will have contribution both from the background of the tip and also from the magnetic field next to the electrolyte. Mm-hmm. So how will we separate this? I don't know. The tip is not coming, is not magnetic. Yeah. No, but if you have so if the anti-center tip sends the magnetic field. Yes. So if I am trying to manage the sample in a different direction, not only the sample is already magnetized. Okay, so we cannot change it, like. Okay. That's why we measured the hard disk, like the hard disk is already like, yeah, this is a magnetic surface as well. So can you re-explain what are the dark So the
There are bright lines, dark lines, bright lines, dark lines. What it means?
yeah, so
Do you have an idea?
so the darker basically whenever the field will be across the field will be parallel to the NV axis, we will have a stronger photoluminescence, and then that will correspond to a stronger aligned axis magnetic field, and then the darker areas will correspond to off axis magnetic field, or basically in the
Means means magnetic fields. What do you think that it represents?
uh, I basically it is my guess, but I would assume it is maybe inhomogeneity in the
No,
sample.
it's not inhomogeneity. It was really a hard disk that we took
Mm-hmm.
from the. It was really from a what?
Magnetic domain.
It's the magnetic domains. So
Mm-hmm.
you see, it's amazing. The magnetic domains is really, really tiny. It's a little bit longer in the other directions because that will provide the signal enough so that they can discriminate or not. But you see, the so these are really the magnetic domains of the magnetic hard disk that you have in
Okay.
your laptop or whatever. It's amazing.
Yeah.
You can see that how this is done. Oh, that was on the computer. So the quality of the thing that they have, and they are able to read that somehow.
Mm-hmm.
It's unbelievable. Okay. And so can you explain me very quickly, re-explain very quickly why we associate this mixing of the state by the off-axis magnetic field to a modification of the photoluminescence? Because basically the advantage of the technique is that we only look at the photoluminescence level.
So basically, whenever there will be a off-axis magnetic field, the spin states will mix, and both the different spin states decay differently.
Okay,
Like
can
the
you
non-radiative,
show it on the diagram? Here?
like here. There will be some like different components. Whenever there will be a different magnetic, like the off-axis magnetic field, the spin states will be mixed, and then basically here the contrast is decreasing with the increasing off-axis magnetic field. So if if the population is present in, like, let's say such significant population is present in both the spin states, then they will decay through both the channels. Like they will also decay optically as well as they will decay through phonon modes, and then they will have different like there will also be some luminescence, but it will be less, and then there will be some phonon modes decaying non-radiatively. So that's how they will decrease the contrast and decreases the efficiency of the ESR method. Yep. Any more? Yep. Thank you.